Yeah. Good evening, everybody. And today I don't want to go through the slide and try to say some theoretical matters on the model. You can read it within 1 or 2 days. I provided two papers, which is the development of the model. One published in 2016, reviewed all the publications regarding to the model, to hydrous 1D, 2D, and 3D, and another one in 2024, which is evaluate again the development of the model and the publication, and you can see, and if you read it, then you will get referred to the right like references. So now I want to pop up the questions, in the real world, and try to solve or answer a question. Okay, this is the problem that we want to solve related to water management. So definitely you have this file. So this is the question. The problem that we have a profile in saline condition, and the government said us that we will deliver like 8,500 cubic meter of water to produce some barley or wheat or whatever you want. So that water includes the leaching requirement and the irrigation water demand of, for example, wheat or barley. So in that region, farmer apply like 20 centimeter for leaching as a pre-irrigation before sowing. 1 month or 20 days before the sowing, they irrigated the lands to become air, to leach the salinity. So try to plant the crops. And it starts from 20 September. And normally they do 5 times of flood irrigation. If we calculate this amount, we will reach to 130 millimeter of water at each time. So the time also mentioned here 5 times. And it was a question that if we change the furrow irrigation to drip irrigation, what will happen and how much water we can save, or would be the salinity or sodicity of the profile differ from the furrow irrigation or not? So you have this file with you, the question, and also the data set. So this is the properties of the profile. We have 4 layers with EC, pH, the texture, composition, SAR, and hydraulic parameters. So provided by the laboratory. And in this table, we can see the composition of each layer, like calcium, magnesium, sodium, chlorine, yeah, carbonate and bicarbonate, and sulfate. And also we have this composition for water and rain. So this is a typical information of the profile. So yeah, we imagine how that amount of water can alter the salinity of each layer and throughout the profile. And yeah, based on that amount of water that the government wants to deliver, we should reach to the potential of the yield, because it's huge amount. 8,000 cubic meters is too much for example, for barley or wheat. So this is the overall description of the profile, and also you have the Excel file, which provided you the evapotranspiration, precipitation, and leaf area index, the potential condition. So we want to use those data. We put to the model, run the model to see what will happen and how we can interpret the results. And probably you don't install the model. In the provided file, you have Hydrus 16 or 17 or both. 4.60 and 4.70. Please, install one of them on your PC. One of them, 17 would be nice. Actually, we can download and get some, in detailed information from PC Progress website, which is dedicated to Hydrus 1D, 2D, and 3D, and all the examples and publication are there. There are several like workshops, conferences related to that model, and you can use that website. Did you install already? Maybe we should go step by step on my computer, and you can try to try flying, and then we can actually this kind of workshop needs like 1 week. So, but in 1 and a half hour, I want to deliver everything, and it's impossible. So, the model itself is really user friendly, and you can just see that just a moment. Here you put all the information that you have on your hand, and this is the post-processing and result of the model. If you click on each window, you can see the results regarding the water content, the flow, the fluxes, and hydraulic parameters, and mass balance and chemical balance of the profile. So if you want to run the model immediately to see if it works and what is the problem, if maybe here we can check also the data set. If you put all the information in the model, if the model doesn't work, we should say, okay, maybe something wrong in the information that we give to the model or the laboratory gave to us already. So in the first window, you know, the model, when we run the model, it looks like this window, and we start from main process. In the main process, we will select water flow and solute transport. If we have all the information of the profile, then which means we have the measure ion chemistry, which means we have all the composition of each layer. So we use that one. Otherwise, if we only have EC or SAR or maybe a tracer, we use the standard solute transport, the second option of the solute transport. So we also the root water uptake. If we want to evaluate the heat transport and root growth, we can check all of them. In the next window, we should define the geometry of the profile, which means we have to define the number of layers and number of mass balance that we want to evaluate, and the length unit and depth of the soil profile. Our profile was 100 centimeters.
Sorry,
and
maybe an ignorant question.
Yes.
Without perhaps an ignorant question.
Yeah.
What are layers?
The layers was pedogenic layers. A soil scientist went to the field, got the profile, tried to describe the profile, and then gave the result to us. Okay? It's, you know, if we go, for example, if we are not the soil scientists, we just want to run the model or take the data in the model, maybe we can give like 20 on each 20 centimeter interval to the model.
Okay, so layers basically.
Yes.
Different depth.
Different depths and different morphological and structural properties. So here we just say, okay, this is 4 layers, and later on we can specify the depth of each layer. So
I have a question.
Yes, please.
You have limited the depth to 100 centimeters, but the profit will be more than 1 ounce.
Actually, you can use it like 2 meters, 3 meters. It depends on the condition. Here we have a free drainage bottom boundary condition, which means doesn't matter. We can take like 2 meters or 3 meters, but we want to evaluate 0 to 100 centimeters, so we took it. In that, you can play with that. You can add like 200 centimeters later on when you run the model. It's already run and put on the file. You can use later, just play with the data to see what will be the result. So
may I make a comment?
Yes, please.
This model is like a church organ, you know, such instrument that has several keyboards and many keys to move, and so what is appears there, it is very difficult to adjust everything. But even a church organ, you can play the stuff that it is now. For only getting the power of the model, you need to have a lot of information. And for the model, you must let's go to the profiling with the horizon, and then there's a called materials in this model. But layers are divisions and because of the computing, it needs to have a lot of divisions. Because if not, changing from a material to another one in a good way, then it will crash. So it makes some kind of transition. That's why it depends from layers. You can take 2 meters with 200 layers and then only having 300. Then from this layer to this,
Yeah, thank you, Professor. Indeed, it is the material. It is the like would say the functional material of the soil, because it's completely different from if you just say, okay, this is the interval that you are saying. So here again, you are specify the time units and the discretization of the time. If you want to evaluate for a longer time, like 10 years, we would specify the final time to like the end of the simulations. And if we want to run for 1 year or 5 years, we have to calculate the time simulation, the end, end of it.
Sorry, I don't know if I missed it yet.
Yeah.
So like the output of this model is the electrical conductivity of the soil, right?
It gives us, yes.
And is there an overall formula that shows which are the inputs and how they? Like,
Yes.
Because right now, like, I'm saying like individual inputs, but I missed the overall.
Yeah, actually, in the beginning, I told you that I don't want to go to the theoretical matters. Yes, it's calculated based on the composition of the solute when we will give to the model as an initial condition. Based on that, it starts with this EC, because we don't give the EC to the model. We just give the composition of the solute.
Okay.
So based on that, it's started to calculate the EC and the EC of the soil. And it's not the EC of paste extract. So here, we want to run the model for 10 years. And so we would use 3,660. And we have the data set for 10 years actually, but when I want to evaluate it, we use the average of those 10 years, the boundary conditions, which means the evapotranspiration or the input and output from the top of the soil, which means evapotranspiration and precipitation plus irrigation. So we want to run for 10 years, so we specified here 10 years. We don't use the meteorological data here because I already calculated the evapotranspiration in aquacrop and ETO calculator from FAO. So you don't need to calculate it, but if you get the meteorological data, you can use it immediately to the model, or you can use in ETO calculator software, which is freely available from FAO, and you can use it. And this is the window of generating the results. And if you regulate it based on the time, you can say after each time, just print it out to see what is happening in the model in the run. And just after that, generate all the data based on this information that we give it here. So I would suggest that use the interval that you specified in the model in terms of the time. So I would use 1 to evaluate every day what is happening.
For 10 years.
For 10 years, yes. Yeah, this is the iteration criteria that we don't, for the moment, try to change them because they already provided some typical values. But if we want to calibrate the model, we have to play with those data and change the sensitivity of the model because if you make it with higher amount and then the tolerance, then the data you get, it's not so precise. So it's based on the criteria, the value that you put here. And
so you calibrated with real world data.
yes, the observation after the time, if you, for example, you do something, you have the profile, you do some strategies, and during the season, during the experiment, you collect some data. Based on those data, you can calibrate the model.
But sorry, do you have to change that? Or
No, for the moment, no.
But normally, do you?
Yes, sometimes we change it.
You cannot use it before.
This is the hydraulic model. Then they have different stories to consider the hydraulic model and the science behind that, and each model has own pros and cons, and then normally people in most of the arid countries, arid region, arid soil, Bangalore is the best, work very well. So in our case, we also use that one. Of course, if you want to calibrate your model, you can play with all of this model to see which one is the best. And there are several publications regards to this equation and playing with some data set to see, okay, mostly Wangel and Muallim works very well, the data. And we don't consider any hysteresis and dual porosity in our system. So here is the hydraulic parameters that are provided in the text file, but they are not measured. They estimated based on the texture and bath density. And here, the Rosetta, the neural network prediction implemented in into the model. And if we go, just check the neural network prediction, this one, and put like sand, silt, clay content. Can you read the values? Yes, for the first one.
40%.
Yes.
37 and clay 23.
Clay 23.
Yeah.
And bulk density 1 point.
We don't have
Take it 1.5. We don't have it. And we use the predict button. It is predicted already. This is the value of theta r, residual water content of the soil, saturated water content at the saturation. Alpha is the shape parameter of Van Gerochten or water rotation curve, and is the slope of the water rotation curve, and case that is hydraulic conductivity at the saturation condition. But and if you I just accept it, and if you have any data, real data, you should use your real data is, for example, hydraulic conductivity. Mostly we have it, but for the rest, estimated from the software like Red Sea or ETC, and here with the neural network. I already put all the information in there. For example, next one, just click on this next row, and select check the bottom of neural network, put some data in it, predict the hydraulic parameters of the layer. So I already did in this file. You have it. So for the boundary conditions, for the upper boundary condition, have you played with the model, with this model, or similar? No? Oh. So what is the boundary condition?
Here I got rocks.
Oh, cool.
Me as well. I'm the only model.
So what is the boundary condition?
Well, that would be, for example, the top boundary would be precipitation, irrigation, and the lower boundary would be groundwater level. Then you have different options. I don't know here, like if you have
Yes.
pressure head or
Yeah, variable pressure head or constant pressure head, free drainage.
yeah, you have various options depending on.
So then we have to specify what is the situation of our profile. Here in our case, we had the atmospheric boundary conditions, which means we have evaporation, transpiration, and rainfall, and water supply as irrigation or leaching, and maybe with runoff. Probably if we put like 10 centimeter, 50 centimeter of water on the top of the profile, then we will have the runoff. So the model calculates that one as well, based on the data that we provided.
So as it is right now, there is no runoff. It's on the surface layer.
If we put the surface layer, yes, we don't have runoff. Because we say, okay, we have a big like area, and we put the border on the around the land, so water stay there. Yeah, and for the lower boundary condition, we have different options based on the if we have a constant water content or constant flux or variable pressure. Probably you have a diver, you put on the borehole and measure some data with fluctuation of the groundwater, then you can select this one, variable pressure head, and put all those data into the model. And the model based on the fluctuation of groundwater level, try to calculate the water content through the profile. And this value is the extinction coefficient based on each crop. And again, in the calibration processes, we can play with this one, and I use 0.39 based on the experience, and also in the literature we start like from 3080 to like 45, 0.45.
What is it meant by extinction?
Oh, I forgot to say something else. If you need to know or try to find out what is it, you can use the help option, the model, and it gives you the hints based on the windows that you are in it. And here you can see you can try to find out what is the boundary conditions. It explains. See? And this is the intersection, and then so again, we can say, okay, maximum head at the source surface, because in our question they said, okay, 20 centimeter as a pre-leaching or pre-irrigation as a leaching they provided to us. So we assume that the layer of water or the head would be 20 centimeters, not more than that, but it reduces by the sun. So here we have to define the composition, what we have in our hand. So we have to use the weighing schemes based on the information that we got and the profile condition. So we have two options, three options, but the first one it's locked because we first at the beginning we choose the major IN3. So we use the Planck Nicholson scheme, and you can change and shift with between two of them to see what is happening to the model once you want to calibrate the model. So you can define the mass unit here. Every the unit that you have in your hand, you can put it here. Later on, if the model calculated, and if you want to convert it to another unit, you have to do by your hand, you know, in the Excel file or other something. We use the tortuosity factor, the stability criterion of 2. And here I define the 6 solution concentration. What does it mean? We had 4 layers, 4 soil layers, and it was the solution composition. We had one for irrigation, the water for irrigation, and another one for rainfall. So we specify because we want to say, okay, we have 3 source of solutes. One rainfall, another one irrigation, and 4 the soil layers. So here, I don't want to go to the absorption and desorption kinetics because it would be very complicated and then took time to calculate. So yes.
So I didn't understand. Within the layer, there is a gradient of electrical conductivity, or the layer is like one number. Do you know what I mean?
Yes. You know, if you
like 6 concentration.
Yes. So normally soil scientists, when go to the field, they collect a sample, not every 1 centimeter. They collect from 0 to 25 centimeter, as a, for example, root 2, or 0 to 40 centimeter. So they mix the collected soil and give the 1 sample to the laboratory. So it's correspond that the data correspond to the specified layer. And here we have to put all the information, the composition of the soil layers and also water content, water, irrigation water, and also the rainfall. You see, here we have 6 numbers that we specified already. We have 6 compositions. And the first, the layers come, and second, we can specify what kind of water composition should be. There are actually the codes. 1 to 6 are the codes for 1 is layer 1, 4 is for layer 4 of the soil, and 5 is for like irrigation water, and 6 for rain. And as I said, I don't want to go to the absorption and precipitation, so we leave it out for the moment. So here as well, it just, and yeah, here is the solute transport and reactive parameters that we have to specify for the layers. There are the bulk density and diffusion water in the soil. Normally, they said, okay, it advises 1/10 of the soil profile should be taken for diffusion, for the dispersion. Sorry, for the dispersion. For the diffusion, it would be like 2 from 2.5 to 1.8. It's dependent on the composition, the temperature. So the dispersion advised to taken as a 1/10 of the soil profile. You can later on play with that if you want to calibrate your model. So we don't have a CEC parameter, and other part the calculated SA. I don't remember by heart for the moment. Would be kind of fractions, yeah. Calcite surface area, so we don't have it. For the concentration, we have to again specify the upper boundary condition, which means it is the flux, the water that we have.
Let's just.
Yeah. Yeah, I open. I don't see anything. Maybe you can check it. Yes, the software is free. You can download it from PC Progress. So for the concentration, for the solute concentration, we can specify the upper boundary condition and lower one. So for the upper, we have the fluxes, like rainfall and irrigation. For lower one, we have the zero concentration gradient, which means we have a equilibrium between the layers within the profile. And because the data set given which given us in liquid phase, so for the initial condition, we use the liquid phase, which means all the data set that we put into the model came from the soil solution. And for root water uptake, as you know, we have different kind of models, and we use Featherston here, and we put the threshold for the solute, and we say, okay, if the EC or the osmotic pressure reach to that value, then the plant experience with some salinity problems. So here we put 1 as the highest value, which means because it was too much water we want to apply, so we want to reach to the potential yield. And here we can use the maximum allowed concentration for the passive root solute uptake. I check 0 for the moment. And this is the parameter of the FEDES parameter, which is provided in the database of the model. And there are really literature review on this matter. And they, the data set got from different literatures. So for example, for wheat or barley, more or less are the same. And they put like, if, for example, reach to the minus 60,000 per share head, so the plant will be done. And here is the like more or less close to the field capacity. And from here, the plant exercises the SLS, the salinity of water stress. Yeah, this is the values that got from the data set. So this window is upper boundary condition or variable boundary condition that we should specify. If we have this data, so we can solve out the problem, you know. In the first column, it is at the time, and the interval we adjusted to every year, every day. So we have like 365 days, 66 days for a whole year. And it started from September 20, I guess so, yeah. And the second column is the precipitation, which we got from, for example, the meteorological station nearby the area. And in the third one, we have the potential evapotranspiration, which calculated based on the meteorological data using some software like ETO calculator. And this is the maximum potential. The fourth column is the maximum potential at the surface of the soil, which means it is huge amount of potential if the water wants to evaporate from the soil if it completely dry. And in the fifth one is the leaf area index, which is given in our example example that it would be the maximum potential, and we derived from the literature like this. You see, this is for example, for durum wheat. This is the leaf area index at the potential condition. Do you see? No, you don't see it. Maybe you have it in the Word file. Can you check it?
What?
The name is NIM. The name is NIM9. It is NIM. NIM29.
So in the Excel file is 0.
Yeah.
What?
Leaf area index.
Zero? What? Here at the beginning of first.
No. The Word file is not the Excel file.
Ah, the word.
Go down, please. You see, we got the data set from this.
Ah, the maximum is 5. We have to go.
The maximum is 5 for wheat or barley. Yeah.
Doesn't Hybrid calculate different or
No,
you have to provide?
we have to provide it. Yeah. Actually, the leaf area index is the data that we have to measure in the field.
Yeah,
We have to measure or
yeah, because someone calculate that, but you have to give plan high.
yeah, because we want to give to the model. Actually, yeah, the models can give something based on the potential evapotranspiration and actual evapotranspiration, because it calculated and provided the actual evapotranspiration. Based on that, we can just estimate the leaf area index. No. So in the 6th and 7th, we have to specify the codes that I said that we gave the code 5 for irrigation water and 6 for rainfall. Here, C top means the concentration at the top, the flux, the concentration of the water or flux at the top, and C bottom is the concentration at the bottom. For the bottom, we should gradient boundary condition, so we don't specify anything. But for the C top, we have to specify the concentration of the precipitation or rainfall and the water which supply. So if the water supply as a irrigation, we code it 5, and otherwise we should say, okay, this is rainfall, and the model understands already that this precipitation is rainfall, and another one, as I show you, this one. You see, it's specified 5, which means the composition corresponds to the 5 that we put in the table. So yeah, when you want to evaluate or do some scenario analysis, you can change these values. You can change the date to see, okay, what time would be the perfect for irrigation and how much water by hand, firstly, and secondly, the model generate, you automatically give the best period of time to give some water to the plant. So far we put all the data, we specified some information in the model, but we didn't define the geometry. We just say, okay, we have 4 layers, but we have to say the depth of layers and then coding them, you know. The model should understand with the corresponding number of each layer to the depth of the geometry. So we will go to at the graphical editor. Do you see? No. This is the graphical editor window of the model. How can I bring the top menu? Bring to the you can provide it. Maybe it's okay. Yes. So if we go to the just the hints, this is the discretization, which is very important in using this model. And once you want to calibrate the model, you have to play with that or try to find out which kind of characterization would be the best, which means if you change it, probably for denser discretization here, which means you have it is more important because it faces to the upper boundary condition. Or if you have make denser here, which means you have groundwater level and then fluctuation, you want to focus on that part. But at the moment, I just put at it is as a normal one. And you see in that window, if we select it as a material distribution, we can specify the depth of the material and give the number. And just put edit condition, just go from the top or any depth of the profile you needed and say, okay, this is for example, the depth of my layer. And here you can specify the code of the layer number. If you have, for example, 10 layers and 1, 6, and 7 were more or less the same, you have to say, okay, for 1, 7, and at the specified depth, coding 1, because it uses the composition of that row we put at the composition solution. So yeah, for different layers, we will specify from we start to just using the edit condition, left right click, and then go to the corresponding depth, just it, and then put the number as a layer. For the roots distribution, normally you have we will have 3 kind of distribution, and if you know already how the root concentrated in the soil. You can specify it here. Yeah, start from 0 with no root and 1 between 100 concentrated the roots in the profile, in the root zone. And here I said, okay, from top, it is 0, reach to like 15 centimeter, reach to the maximum density. And from that, it gradually reduces the density of the root. Yeah, for this solution, initial solution concentration, once we put the layers, we use the major ion chemistry. So the model immediately goes to the condition, the values that we put in the model. We said, okay, this is the initial condition of our profile. And here you can specify the location or points that you want to evaluate from 1 centimeter, 2 centimeter, 3 centimeter, 10 centimeter, or 15 centimeter, 50 centimeter. If you want to say, okay, I just want to see what is happening through this 50 centimeter, just put 1 point here. And how you can do it just by clicking on the insert and put like everywhere you want. See? I added another one. And for the delete, yeah, you can delete it if you don't want to evaluate or consider the deeper part of the lake. So that's it. And just save it. You see it? Yes. Below this one. You see, once we start to save the project, then the post-processing or result of the previous one deleted already. So now the model is ready for run. We just run the model to see what is happening. You don't see the window here, but I can see what is happening. Some numbers, some route. Let me share if I am so fast to see. You see, the model is calculating and it's reached for like 3 years, 4 years. And they start to calculate everything, every solute concentration at the points that we specify for 4 points every day. And we should see the result, what is happening. Within more like 2, 3, 5 minutes, we will have some simulation for 10 years. Actually, we can do it for drip irrigation. We divided the amount. We should calculate how much water if we want to use the drip or tape as a different irrigation system. So the amount of water should be calculated based on each dripper. And so we have to know how many drippers we have in the field. Just do it and compare with the data set that I provided you. When the calculation is finished, you have to hit the enter to save the result. So I again share the the model to see what is the result, the initial result, and later on we can make some graphs. You see, this graph is the pressure test based on the applied water during growing season for 10 years. The fluctuation is for 10 years, and if we want to like edit the chart to see what was happening for this year.
The different colors represent what?
Different colors represent for the different depths of different points, the depth of the points that we put in the graphical editor. Which means we have I have to add the legend here. You see, we had 5 nodes, and the first one is 1 centimeter, the second one like 10 centimeter, the third one like 15 or 20 centimeters. And it gives the exact values of that point.
The red one is
the 50 centimeter at the middle of the profile.
And it's 0 most of the time.
Yes.
Because that's where the actual is.
And this is also the water content. You can see for the deeper layer, we have more water. Do we give too much water to the profile, to the soil? Let's see. This is the result of the first year. The water content.
The green one is often saturated, completely saturated.
The green, actually the green one, the red one is correspond to the 50 centimeter. The green, light green, this one, like for 40 centimeter, and that was 30 centimeter. Which means the deeper layer, more or less saturated and has too much water in it. But at the top, we have like 50%. Yeah. Fluctuated in during season. This is the water. You see, these peaks are the irrigation amounts.
But there
we
are
have
some times that there are too much irrigation.
Yeah.
In those peaks very high.
Yes.
We're irrigating too much.
No.
It's fine.
It's fine. It reached to like the saturation condition and immediately went down. So it happens for everywhere. Once you give some water as irrigation, the water, the soil will saturate it, so goes up and then came down. But you can see at the deeper layer, the water content is at the optimal condition. A little bit more than feed capacity. But here the scenario is that we gave too much water. No? So this is the first result that we want to evaluate. And this is the information of the profile. Throughout the profile, what would be the pressure head, what would be the water content in whole profile, regardless of the points that the nodes that we specified in the model. So I don't want to go to the post-processing because they just give some general idea of the results. I want to introduce you how you can use the data, the generated or simulated data, which of this, for example, project, and try to calculate further or make your own graph, because it doesn't give you the EC value and SAR value. So if we go to the directory of the project, we can see the you see, I run the model here in this directory, and once you save your project, you will have the Hydrus extension of your project, and also a folder. If you go to the folder, you can see several words or like text extension, and there are the input data like atmospheric. Everything that we put into the model is separated here in different files. So for example, if we go to the observation chemistry to see what is happening to the salts, I just opened it and I should share the yes. You see, this is the time variable, and after each day, the model calculated the calcium, magnesium, potassium, alkalinities, sulfate, tracer, chlorine, and EC and SAR of the layer. And you can see based on the data that we provided for the like not who is the located in the first layer, and the model says okay, the EC value as the initial one is like 32 decisiemens per meter, and SAR 60. Can you check it with the table that I provided? It should be more or less the same. Yeah, it is the same as you know, because it's top of the layer. The value is the average value for a whole layer. But here, once we have at the top of the layer, and it's exposed to the evapotranspiration, so we have a higher value. So yeah, again, we have the values for the second node, like for like 13 centimeter. And all the information regards to the solutes are generated here, and you can evaluate the solution, evaluate the like exercises and your scenarios here. You know, the 17 was the node of the deeper layer, not 15. So if you put all this data, just import the data to the Excel file or any software that you want to use, maybe R or other things, to make a graph. Yeah.
Sorry. Can you please line solid concentrations that will fit the model?
Yeah.
is this model assuming that they are going to, it's constant?
Constant what?
I mean, we are predicting over 10 years with those values. And then we are going to make, I mean, we are going plans, we are doing soil management. These things are going to have impact on these soil calculations as time goes. But does this model take into account these factors?
Yes, we have to specify this management into the model. You know, it's run the model based on 1 year. The information of 1 year and it's not like 10 years time. But if you have like for the data set for whole 10 years, with different management, you can put all those data to the model to simulate it.
And then, sorry. And the mental models like this, there are always assumptions, underlying assumptions. Can you tell us what assumptions this model works on?
You know, in the modeling approach, we are simplify the real conditions, the system. So sometimes we say, okay, here we just have, for example, a vertical direction. We don't have any lateral, but in reality we have it. Yeah, if we have a preferential flow, so everything completely different from this. But we can evaluate it using the model. But we have to define in different way the model, what we want to evaluate. Now, if we change the water content based on, for example, based on the drip irrigation or change the date of irrigation, of number of irrigation, you will have different results. But if we make a graph for EC and SAR for example, for 10 years, for 0 to 50 centimeter, we would see, we want to see what is happening. And I did it already in the Excel file that I provided you. Let me again share that. No. Yeah. Yeah, okay. But I actually I have to use, shall I use it here? Okay. It's yes. You see, I just imported the data from the CSV file, the text file, it's generated by the model. And yeah, here I just calculated the average value of soil EC from 0 to 50 centimeters. And it says that at the beginning, from 0 to 50 centimeters, the EC values were like more than 50 decimals per meter, and reduces immediately for after the leaching. And during the season, it fluctuated based on the irrigation water and crop demand. And in summer here is the summer period, and again it's went up.
But is there any input of solids from the irrigation?
Yes. You see, I explained that we coded 5 as a composition of irrigation when we put all the information into the model.
But in this case, it's like not really salty, so like when you irrigate, it's just going down.
Actually, the EC of water was like 1.3 decimals per meter. The water
So
was
over time, should it increase because now like it stays constant over the time on those.
Yeah, it means that if the farmer traditionally use the furrow irrigation with that amount of water, so they won't have any problem, and that their system will be sustained regarding to water content, water management.
So the salts inputted by the irrigation, they will go
Down.
After 1 year.
Yes. Otherwise, if go up, so they will have some problem. But if we change, you know, it's interesting when we change the scenarios to drip irrigation, we get completely different results. And can you guess what will happen? Changing from furrow to drip irrigation. The same amount of water. 20 centimeters as a leach.
Ah, okay. Always doing the first leaching and then
yes.
Either furrow or drip.
Yes. And here we can see the SAR for the profile 0 to 50 centimeters. If you are interested, just play around with the model to see what is happening, and don't consider for the calibration, because first you have to learn how it works and how it's sensitive to the parameter and which parameter is most influence or impact will impact on the model. So just try to adjust them to find out what would be the best option.
I don't know if it's feasible, but would it be possible to really like launch at the beginning with a lot of water to flush out the source, and then the upper threshold is no longer can
we can do it, but it's based on the availability of water, and in reality we can't, you know, you have to make a big border surrounding the field and like put like 1 meter or half a meter of water. It's too much water.
The leaching is every year.
Every year, and at that region they use before the sowing and just after the harvest. When they harvest, they try to irrigate the field, so they leach all the salt with that they came out. So and during the summer, because the water is unavailable, so the evapotranspiration, the potential is so high, but there is no water to evaporate it. So
and then we could assume that since there we're just assuming the first year leaching, not
no,
years.
every year it's leached, you know, because every year, you know. Yeah, I think in the first year we have a higher value of salinity and solidity. Let's say, yeah. After first year, because every year we use
then
that.
should be going
Down.
I mean,
No.
yeah, it doesn't go up.
Yeah.
Maybe the mass of solids is the same, but during the summer there's less water, so the TSQ is higher.
Yeah. And imagine what is happening when we use the drip irrigation. This is the result for drip irrigation. Let's check because yeah, they should check the passes here. Looks like the maximum was 50, yeah? 50?
Yeah.
How is it? Let's just copy it and put next to the.
Make sure in the soil, when the water is just water and drop in the soil, and then the soil can be water.
Yeah, this is furrow, no. We should. Yes. This is furrow and this is drip. Can you compare these two figures?
Back to the right.
Yes. Here is the result of drip irrigation and this one for furrow irrigation. The EC of 0 to 50 centimeters. But what do you notice?
The upper threshold is higher.
But I think there is no water that is being used to reach the soils.
Actually, yeah, that's true. During the summer, the EC value goes up. Then once using the drip irrigation, and imagine if we, because it's not constant in one location. Every year it changed the location. And around that, because we have the waterfront and redistribution and the accumulation of salts around each dripper. So once the drippers change from a location to another location, the EC value will not be the same as the initial value that we put into the model.
The down value means the down value.
How is it? It is the same.
Have the this one 500 and 500.
This one?
Yes.
No, they are the same. They are the same. They are for 10 years.
I mean, depend for what? Not to get.
What does that axis? What does that
Average of 0 to 50 centimeter of EC. This is EC of soil and also the can you see? These together are EC of water, of soil, from 0 to 50 centimeter. And these values, the fluctuation. Here, when we put some water or irrigated the land, the EC values went down from here. When this is the pre-irrigation, it started from here, and the EC immediately or after 2-3 days went up, like 2 to 5. And during the season, we had some irrigation and fluctuation of EC. And here is more or less the harvest time. And here the summer time. During the summer, the EC value goes up, but not reach to the value that we were in the initial condition. The initial condition was like 25, more or less. 21. 21. But yeah, it reached to 11. You see? And for the second year, the initial condition will be like 9, which means every year we need less water to manage it. So if we want to optimize the water management, we see, okay, how much water is needed for leaching, how much water is needed for irrigation. You have to evaluate this value. If the criteria will be the EC and SAR, you have to evaluate those values, those characteristics of the profile and say, okay, this amount of value would be the optimum, and you will deliver to the farmer. Or maybe later on try to upscale at the like plain scale to have some such idea which part of the region should have should receive more water and which part less. Is there any question? I'm ready to answer you. And
which crop was planted?
Here, as an example, we use wheat.
And that with handle that amount of the stream?
We don't have any essence.
No, like the soil EC is
Soil EC is less than for during the growing season.
The growing season winter.
Yeah, it's winter, summer. Winter, summer.
So 5 will be the maximum.
Yeah.
So if you would like to lower even more, you will have to add more leaching, basically.
Yes.
Okay.
Can I ask something, Meisam? With the dose that you put, the 5 doses you
Yes,
had,
yes.
Observation.
We call it the observation nodes. Yes.
Okay, so if you put more in between, do you increase the accuracy of the model?
No.
No.
No. You know, the model calculated based on the discretization once we specify. Now we have like 100 centimeter of discretization, 100 run for every node. Yes, but it generated data based on the observation node that we specified. Otherwise, we will get like millions rows of data. And one more thing I would add is that it was the direct or forward simulation of the model. I want to introduce a term of inverse solution, which means if you, for example, do some management, some treatment in the field, and collect some, put some sensor like water content sensor or dye well for the groundwater, and those data will be your observation data. So once you use those as an observation data and run the model, and based on the observation model, try to train itself to reach to the observation data. For example, for EC, for example, for water content. So in that way, model automatically calibrated. And there is an option.
Those is for a specific area. So every time you need to do it for a specific area.
Yes, indeed. And it's just the simplest scenario and exercise that we can do with this model. We can evaluate the particle transportation within the profile. And also if we use the 2D or 3D, because the 1D is freely available, but for 2D and 3D, it's commercial one and we have to pay. So using the 2D and 3D, you will get too much information and the understanding of the situation, and our colleagues asked us what was the assumption. So you will see the flow, water flow laterally, vertically, horizontally. And I explained a day before in my poster that we use this kind of model, this kind of stuff, and then calibrate it based on the EC value that we observed in the field during a growing season. And we found out if we reduce the frequency, the duration, the time from 30 days to 50 days, we will get a better result, better yield. and the model doesn't provide us the yield, but it gives us the actual transpiration. And we divided actual transpiration to the potential one, and we can evaluate the rational yield of the crop. Okay,
I think there's one question.
Yeah, this one. So, unless you fit observations during the 10 years periods, after the first year, the simulations are not really useful because they will be the same.
Yes. Yeah. We just evaluated to see what will happen in 10 years. And there is another option, because here we just put the data set for 1 year. If we have the whole data set for 10 years, we can put all of them into the model as a variable boundary condition, and definitely we would have different.
If you ever validated with a few experiments?
Yes.
Yes.
You know, when we went to the field, like in 2020, it was a plain, like 46,000 hectares. And some part of the area, like the farmer left them out. And I asked them how long it took that this land like become like this, like a desert. And they said, okay, we can't use it. It's impossible even with like 1 meter as a leaching, use this farm again as for the irrigation purpose. So they said, okay, maybe 3 to 6 years. I try to simulate based on the some data that I had at that moment. And I said, okay, after 4.5 years, you lose all of them. Your land will be degradable. So, and it took like 5 years or even more to bring it back to the situation that it was. You know, this is the another thing of the evaluation or land degradation evaluation.
Can I ask something? Well, since it's a model, do you report how accurate it is or the probability of the model to be right?
Yes. You know, yeah, I said it is the forward, just a simple exercise. But once we have the observation, for example, we choose or select some pilots, collect some data during the season and put into the model. So based on the offset, between the offset and simulated, we can say that this is kind of the accuracy based on the statistical analysis. Yes. Yeah, so I think it would be enough.
Anyone? Any question?
Maybe a last
Yes.
At the end, I didn't understand why with the groupification we have higher segment. Because we said you move the grid, but you don't consider that in the law.
What consider? I consider
the grid.
No. No.
Yeah, but why we have higher segment in the
You know, drip irrigation, the water didn't go down. It's say like 0 to 10 or 50 centimeter. And during the summer, water is available, evaporated, bring some salt up.
Because there was less water in the soil.
Because it's not infiltrated deeply, percolated to the soil.
And using the same amount of irrigation.
Yes.
What is the rest of the?
You know, yeah. Potentially, yeah, I would say that it is evaporated.
Okay.
Instead of going to penetrated to the soil. Here we have the both free drainage. In that case, water goes down, went down, and reach the soil. But here, as you remember, our colleague told us the transient salinity. So here we can understand what is happening. Yeah.
Well, thanks a lot, Meisam. It was really interesting.
At the
presentation.
end of the end, you know.
Jorge, thanks a lot as well for the presentation. I think you all enjoyed the training school. It was really interesting.
Yeah, if you have any question regards to the model, or if you want to calibrate based on your data, just send me an email. So I try to solve the problem, answer your question, and or maybe connect you to the right people to help you.
Thanks a lot.
Thanks.